So now we're gonna start chapter 10, which focus on, well, not equilibriums anymore, but on limit cycles. So in this chapter, we talk about the occurrence of a closed orbit, or the so-called limit cycles, along with the important Poincare-Bendixen theorem. We start with some simple examples. This is 10.1. Introduction with some simple examples. So first of all, what is a limit cycle? I give a very simple description here. Well, it's just an isolated closed orbit or closed trajectory on the phase plane. Isolated means the neighboring trajectories are not closed, okay? The neighboring trajectories are not closed. They either spiral toward or away from the limit cycle. So we have a few different scenarios that I'd like to briefly describe. So here we have a closed orbit. Let's assume it moves this direction here. So we have the x-axis, y-axis that I didn't sketch. Let's say on the outside, the trajectory will be spiral towards it. So it's getting closer and closer. I mean, not touching it, but getting closer and closer to it. Inside, there is also a trajectory that's not closed, but approaches this limit cycle as well. So in this case, every trajectories, okay, all the trajectories, they are all moving close to this limit cycle. So obviously, we're gonna call this a stable limit cycle, or attracting. Here is a repelling or unstable limit cycle, where it starts somewhere, but it's spiraling inward, moving away from it. Start somewhere close by, it'll spiraling away, okay, spiraling away. So this is an unstable limit cycle. Or repelling. And then we have the third case, where part of it may be attracting. So on the outside, say it's spiraling towards the limit cycle, but inside, it may be moving away. Okay, maybe moving away. So I guess we call this half stable. Okay, and now let me show you some examples where we have limit cycles. The first example is what we call a self-sustained oscillation without external periodic force. All right. Self-sustained oscillation without external periodic forcing. And the equation is put into a polar coordinates. Okay, the equation is put into a polar coordinates. And here is how it looks. Let's look at this equation here. This one obviously has equilibrium points at the following x stars, sorry, r stars, when r is 0, when r star is 1. Okay, so r refers to the radius here, okay, the radius or distance. You can also do a phase line analysis on r. Say this is r here, r is 0, and r equal to 1. When r is between 0 and 1, when r is between 0 and 1, r prime is always positive. So remember the phase line analysis? This is the graph of the right side. Between 0 and 1, the right side is positive. So r is always increasing. If r is bigger than 1, however, if r is bigger than 1, this term will be negative, okay, it's down here. And r will be decreasing. So this implies r star equal to 1 is actually stable. And r star equal to 0 is unstable. Okay, unstable. So r equal to 1 corresponds to an xy, corresponds to a circle on the xy plane. So it turns out the behavior of the trajectory on the xy plane look like this. This is r star equal to 1, okay? This is the limit cycle. This is a limit cycle. Now theta prime is always 1, meaning this angle here, meaning this angle always increases at a constant rate. And outside, it'll be attracting, okay, r equal to 1 is stable. It'll be attracting to r equal to 1. Okay, anywhere else it'll moving closer and closer to r equal to 1, so spiraling towards r equal to 1. Okay, spiraling towards r equal to 1. And r equal to 0 is unstable. Anything starting close to this point, it'll spiraling away, okay, spiraling away. At the same time approaches r equal to 1. If you start somewhere around here, as t goes to positive infinity, it'll approach this r equal to 1. When t goes to negative infinity, okay, that goes to the origin. Alright, that goes to the origin. So in this example here, we have a limit cycle, which is actually the unit circle here, okay, which is the unit circle here. That happens to be stable. That happens to be the stable. Example number 2. So you can use a phase portrait plotter to analyze the so-called van der Pol oscillator. And you guys can dig out some background on this system here. The system form look like this, where x is the displacement, okay, y will be the velocity, so we set x prime to be y. Y prime is given by this equation here. So we don't know why this one will have a closed orbit or limit cycle, or when it'll have a closed orbit. But this will be proved later, okay? So the proof of existence, so the existence of limit cycle will be proved later. But here, I will simply take mu to be 1.5. We try to plot the face portrait, use online plotter, and here's roughly what we came up with. Okay, here's roughly what we came up with. There is a closed orbit that looks like this. It's not exactly a circle. Looks something similar to this, okay? I can't exactly make a very precise sketch. You can use your software to try to plot this, okay? So this is a closed orbit that rotate clockwise. This is a limit cycle, okay? It's a limit cycle. And outside, start from any random point, it'll be attracted to this limit cycle. So every trajectory will move closer and closer to this one, to this guy. Inside, start somewhere from here. It'll also be approaching the limit cycle. So eventually it becomes almost in the same shape of the limit cycle. Okay. So these are the two examples. Like I said, take this system, try to plug in a few different mu's, including negative mu's, and see what happened to that system. All right. So that's the simplest example for limit sets. Simplest example for limit sets. Next, I want to show you a few examples where limit cycles are impossible. Okay, limit cycles are impossible. So this is so that was a short section. Okay, that was a short section. Try to give you some examples where we have limit cycles. 10.2, we talk about ruling out limit cycles. I want to show you the system that does not have limit cycles and also why. Ruling out limit cycles. The first case is the limit cycles are impossible in a gradient system. That is a system that looks like this. Any gradient system, it just does not have limit cycles. So if you go back to 9.3, where we studied the gradient system, you will see this proposition that's also in your textbook that says, let Z be omega limit point of a solution. In other words, when t goes to infinity, the collection of Z, okay? Then Z must be equilibrium. It'll be a single equilibrium instead of a limit cycle, instead of a closed orbit. So that's this proposition. So this conclusion right here that we had actually come from that result. So I want you guys to check that part out. So if some people ask you, hey, show that there is no periodic solution to this or limit cycles. There are no limit cycles for this system. So even though the right side appears to be some kind of a periodic function here, we might suspect that x and y can become periodic as well, but that turns out not to be the case. There are no closed orbit, there are no limit cycles. The reason is actually because this is just a gradient system. In fact, this function is negative x sine y. You can easily verify that this phi satisfies this system here. When you plug in phi here, you do negative dv dx. Yes, you get sine y. Y prime is do the dv dy, you get x cosine y. Yes? So that's the function that'll make this take the form of the gradient system. There's no closed orbits or limit cycles, so these are the same concept. So, all right. So just keep in mind, any gradient system just does not have any limit cycles. And then case number 2 is if there is a, you can create a Neopolov function, okay? Using Neopolov function. Case number 2. Either I use v of x or L of x. So this x is really two variable, x and y, okay? Number 1, it needs to be positive definite for all x that's not the same as equilibrium. And v reaches a minimum at x star. Number 2, the time derivative of v with respect to t is negative for all x that's not at x star. Then x star is asymptotically stable. Okay. So essentially phi is a surface that's always positive except at, well, x star. And the time derivative is always negative. That makes any trajectory will move towards x star. Okay, any trajectories will move towards x star. And now I'm going to show you a quick example on how do we create a Neopolov function. Simple one. So this is a relatively simple looking system here. We're going to try to create a function that's Neopolov. So obviously this guy has the only equilibrium is at 0, 0, okay, 0, 0. So I want to create something that's always positive, away from 0, 0. So it's very easy to picture. I'm going to make some choice with a combination of x squared and y squared. And actually I put an a in the front. That's something we need to decide later. Where a is a constant to be determined, because I need it to satisfy the time derivative to be negative. So phi here, okay, this guy, if a obviously is something that's probably going to be positive, because I need this one to be strictly positive. It is also 0 when x and y is 0, okay, so it is 0 at the equilibrium. But I also need to calculate time derivative and make sure time derivative is negative. And when I do time derivative, applying the chain rule here, so dx dt, we get something like this. That's 2x, okay? Differential with respect to x, get 2x. And this is dx dt. Dv dy is 2ay. And this is dy dt. So fill this out. So we have a middle term minus 2ay to the fourth. So think about what kind of A we're going to choose to make dv dt to be negative. I mean, this is strictly negative. This is also strictly negative if A is some positive number. I just need to make sure this guy is 0, okay? I just need to make sure this guy is 0. So the A we're going to choose is choose A to be 4. That'll make this middle term disappear. That is strictly negative. Strictly negative for all xy that's not at the equilibrium point. And because of this, we can say this is the Neopolo function we created. And all trajectories approaches where? All the trajectories approaches the origin. As t goes to infinity. Alright, so all the trajectories will eventually approach the origin, and that's why we can say there is no closed orbit. Hence, there is no closed orbit or limit cycle. Alright. So these are the two cases where you can actually rule out limit cycles. Alright.